You're good? All right, so we have recording. We have a second talk. And so just a little bit of an amusing point to me, at least, was the very first talk that we ever gave for Boston Haskell was me about 4 or 5 years ago, talking about Comonads. So.
Passing the torch.
Here you go.
Well,
Comonads are yours. You're welcome to take over the whole space.
Well, so that was long before I had ever heard of the word Comonad. So I'm Kenny. I'm a senior at Brandeis University, and what you're going to see tonight is a bit of my thesis project. So just a couple of weeks ago, I was talking to Dominic Orchard about Comonads, and he told me that there's this curse which afflicts people trying to publish papers about Comonads, which is to say that while it is easy to publish papers about monads, it is co-easy to publish papers about Comonads. So I hope to break that trend.
Is he one of the authors of the bonfire bananas?
I
No.
don't think so.
Dominic has been doing, he did the Codu notation,
Oh,
and his thesis was all on Comonads and fun stuff under term.
It is fun stuff. So anyhow, this journey that I'm going to talk about started a while back when I was reading this really cool blog post by Dan Paponi about Loeb's theorem and spreadsheet evaluation. So Dan shows...
Is it a theorem or a paradox?
He calls it Loeb's theorem.
Okay. Okay.
Yeah.
it is an actual theorem. I thought it applied in classical logic.
Okay, go ahead. Sorry.
So what he does is he shows this function, and I'm going to explain this sort of background of this function in a second. But you've got this Loeb function, which takes a list of functions from list, or rather, it takes a functor of functions from functors containing a's to a's, and gives you back a functor containing a's. So one example of this would be if I put in a 2-element list that's got the length function, or 3-element list, sorry, that's got the length function, the grab me a thing at index 0 function, and the add things at indices 0 and 1 function, then that should evaluate out to 3, 3, and 6, because length is the length of the list, the 0th element is the length of the list also, and the 3rd element, or the 2nd element, since I was doing 0-based indexing verbally, is the sum of those two things. But, on the other hand, if I take the length of this list, and then the sum of the length of the list, and then the sum of all of the elements in the list, well, then I'm going to end up doing 2 plus 2 plus 2 plus 2 for a while. So, at about the same time, there was another blog post by Dan Paponi, so thank you, Dan, for sparking this whole project that I've embarked on for the last 6 or 8 months. He talks about how evaluating cellular automata is comonadic. This idea of a neighborhood, that every evolution, every time step in a cellular automaton is determined only by the cells that are local to any given cell. So he shows this generalization where you can have an infinite universe of cells and talk about the evolution of that automata universe using comonadic operations. So I'm going to get to what is a comonad, but the intuition is it's something that whereas a monad is a context in which you are doing a comonad is a context in which you're performing a computation. A monad is, well, a co-context in which you're performing imputation, right? So, Clearly. So we've got this Loeb function where every function in this structure gets to refer to the eventual value of every element of the structure. You get to see the whole future of this structure and use it to pull out and figure out any individual element of it. So like if we back up to here, length is looking at the length of the list, which is going to be constant, because we can't change the shape of something only using fmap. Bang bang 0 is referring to the eventual value of, once we've evaluated the length of the list, we're going to reference that. So the observation is that this is like spreadsheet evaluation. And Comonads, so spreadsheet evaluation rather with absolute positions. And Comonads allow us to talk about relative position within a structure. So these are almost the same thing. And what I wanted to try and do is unify the two of them into something that was tractable to actually work with. So for those of you who are familiar with monads, but co-familiar with comonads, I'm going to talk about monads in terms of return and join rather than return and bind, because it's a lot easier to talk about comonads in terms of co-return and co-join rather than co-bind for the purposes that I'm going to be doing things with. And so whereas a monad, you can always inject something into it, and you can always take two layers of structure and collapse them down to one, a comonad will always allow you to pull something out, and it will always allow you to take one layer of structure and turn it into two layers of structure. So this is going to provide the framework in which we're going to be performing all sorts of interesting spreadsheet-like computations. So notice that maybe as a monad, because you can always collapse two just of A into just A, but it's not a comonad because you can't extract anything from nothing. If you've got nothing, you don't have something. So the particular flavor of Comonad that I really want to talk about tonight, and like we're talking about optimization in the last presentation. This presentation becomes more and more specialized as I go down through it, and I'm very interested in hearing about other comonads that people might want to see slotted into this framework, because there's a sort of family of comonads that I end up describing and doing all sorts of interesting manipulations with, but there could be a lot more interesting things to do than that.
For what it works, I have a streams package that has about 20 other different variations on stream, including that one.
All right, so I will have a look at that. But this stream is just like a const list, except there's no nil, so you're forced to have it be either infinite or contain bottoms, and I'm not going to talk about bottoms right now. So you can take the head of a stream, you can take the tail of a stream, you can iterate to form an infinite stream, and all of these are total functions if you pretend that Haskell is a total language, which a lot of us like to do. So out of these streams, you can build something that is a little bit more of an interesting computational context to be working with. If you have a stream going this way forever and a stream going that way forever and a single element here, then you have effectively an infinite tape, or I call it a tape because it's like a Turing tape. It's infinite in both directions, and I can pull myself along in this direction by taking something off this stream, sticking in the middle, taking that thing, putting it there, or I can pull myself in the other direction. So I can just slide the focus along this one-dimensional line of A's. And that's what this is talking about. And I can generate one of these objects just by using the iterate function from streams to unfold into a big tape. So tapes are a comonad because you can take a single element out of it, and you can create a doubly layered structure if I have a single tape. So if I've got the tape containing all of the integers, going left it's all negative numbers, going right it's all positive numbers, and 0 at the center, then I can duplicate that structure out so that I get a tape of tapes. And what you get is something that looks like diagonalization, because if you work it out, what follows the Comonad laws, which I haven't put up here just to keep the presentation moving, is that if you duplicate a tape, what you have to have is a tape such that if I move left in the outer tape, then I extract, what I get out is a tape such that the read head has been moved left in that tape. So you end up with a space where all of the values go in, where the same value is going along a diagonal in the space. So back to Poponi's lobe function, because this is really what this is all about, is computations that are sort of shaped like this function. Where he gets this function from is he takes this theorem from modal logic, which looks like this, and he says, well, what's box? Well, let's let box be a functor, and see whether we can actually define a function that has that type signature. Let's do some type sleuthing. I say box could have more structure, and what if we, what's that?
I said most modalities do.
Right. So, if box has more structure, say if box is a comonad, well, every comonad is a functor, but what if we actually took advantage of the comonadic structure? Like, rather than just saying, oh, well, okay, it's a comonad, let's do exactly the same thing, what if we write a function that could only be written if box were a comonad? So, a brief interlude is I want to rewrite Poponi's function in a little bit more of a useful way, at least for my purposes, which is to say I'm going to define it using an explicit fixed point rather than his implicit fixed point here, just because I'm going to be using fix all over the place, and the symmetries are a lot more apparent if you look at it this way. So, is everyone following this transformation to this other definition of this function? Does this make sense? So,
I was just looking at the actual modal rules of inference for the modality involved, and they are Comonad apply.
Really?
Yes. The actual modality that is, like, you actually picked the exact correct modality.
Oh.
Right.
Well, that's cool. That is really exciting.
I'll give you the result for your paper.
Okay. So, we want to find something that's the equivalent of the lobe function, but for comonads. So, question mark, question mark, question mark, question mark. So, looking in the Comonads package, which somebody here I think wrote, I don't know, he might be sitting here. There are these two functions. One of them is cfix a la Orchard, and the other is wfix a la Menendez. And these two are almost what we're looking for. Except for the mystery function that looks like lobe has the W on both sides, and we only have the W on one side or the other. And here are their definitions. So one possibility of a function that actually has this signature is fmapwfix.duplicate. It type checks, so it has to be right. But, well, because we were just talking about optimization, and one of the things that we were talking about with optimization, one of the things at the very, very beginning of that presentation, was something to the effect of choosing the right algorithm when you notice that something is slow. So let's just do a tiny little test where we try to count to 10,000. This shouldn't be very intense of a computation, really, should it? So, it's not really my favorite sort of computation. It's probably quadratic, I think, which is not fun. So why is this happening? Well, if you look at the definition of wfix and you look at the definition of our possibility, then there's no sharing going on here. The computation is shaped like a tree. Even though we could share these possible results, every time we compute an element, we have to compute the whole rest of the computation all over again. So we count all the way up from 0 to get each successive number in our sequence of iterated numbers. So it's at least O of n squared. And in a higher dimensional space, if we had a comonad that was 2-dimensional or 3-dimensional, which is stuff that I'm going to be doing later in this talk, the cost would be exponential or worse. So this kind of really sucks. And the root of the problem is that wfix can't be expressed in terms of fix at all. Now, for you smart Alecs in the audience who are going to tell me that any recursive function can be defined in terms of fix, this is not what I'm talking about. Specifically, what I'm talking about is that wfix is inexpressible in terms of fix on its argument. And this means that it's inefficient because there's no single reference to the eventual future of the computation. So the epiphany here is that any efficient evaluation function should look like this. And you know, I've written this function in this way because there's this really awesome feature of GHC 7.8 which is called typed holes. So this is actually something that I can plug into GHC and say, well, I've got this bit of a function and I know what its signature ought to be, so let's try to fill in the holes. So I've cleaned these error messages significantly because GHC is a little bit verbose. So found hole with type WA to A. WA to WA, not very useful. But I'm guessing that we probably have to duplicate something in order to get what we're looking for. So I'm just going to throw that in there and see what happens. And now it's kind of an interesting thing because this looks like join, but we don't actually know how to join an arbitrary comonad. So there's this other thing. There's this f's. We're not using the f's. So let's just throw that in there and see what we might do with f's and whatever we get back after duplicating something. And now this looks kind of interesting because instead of having to have something that looks like join, we have to have something that looks like apply. And there is something for that. It's called Comonad apply. And if we just swap that in there, then there we go. This function type checks, this has the signature we're looking for, except for the addition of the apply. And so Comonad apply is, Comonad is a superclass of Comonad apply. So when I say Comonad apply, I get Comonad as well as the apply operations. And this works! Yay, type inference! So, with this new definition of evaluate, let's actually try to count to 10,000 again, just to make sure that we're actually on the right track. And when you time this, it's just super fast, as we'd expect. Just a slight aside is that when you take 10,000 of this list, it's a little bit faster because this might actually not be true because we were just talking about GHC not fusing things necessarily, but
Very likely. Well,
it might be fused, and it's slightly faster, but it's not significant.
Yeah, the case there was that the reverse itself doesn't.
Oh,
isn't a good
reverse
consumer.
won't be fused, but this probably will.
Yeah, take will.
Yeah. And because evaluate is doing a lot more general things, and because it's not specialized to a particular comonad, there's a little bit of overhead there, but it's not particularly significant. So, wait a second, I just used this whole Comonad apply thing, but I didn't tell you how Comonad apply is actually, what it actually does, or what it is. So here's the instance for Comonad apply for tapes. Wait a second, that relies on the Comonad apply instance for streams. Oh, well, you know, there you go. Okay, so here's the applicative instance for streams. You can ignore pure because pure isn't a part of Comonad apply. And you can see that the apply method for streams just zips together a stream of functions with a stream of arguments. But then, what am I actually talking about when I say Comonad apply?
Black symmetric, yeah.
In other words, Comonad apply is to comonad like applicative is to monad. So
It's very close. There's a little bit of a difference. So this is just a bit of a technical aside, which
Sure.
is that what Comonad apply says is that the app-like thing that we have for Comonad apply respects extract in much of the same way that pure is respected by app.
right.
Okay, but there's not a if you were to look for a direct analog for applicative to monad, you would get like a co-applicative that would require us to have co-exponentials or something that we just don't have.
And so this is what I wanted to. That's very similar to what I wanted to talk about here because in the applicative class, you can have an applicative instance for lists in two different ways. One that zips them together and one that takes their Cartesian products. But here, these laws imply that app for comonads has to be zippy in some sense. That you can't do the Cartesian product trick for comonadic apply. And to sort of drive this point home, in the essence of data flow programming, which is a really, really cool paper by Ustalu and Vene, they don't define Comonad apply in terms of this app function. They define it in terms of what they call czip, which is, it's a leading name. But kind of an enlightening exercise is that for an arbitrary functor, you can show how czip and app are just the same thing because you can define them in terms of each other and fmap, which you have because Comonads are functors. So the zippiness required by the laws of Comonad apply leads to the computational zippiness that we can get from evaluate. Because you can zip, you can zip. So the question arises, I think, can going fast be totally safe? Because we just made these computations super duper fast because we're doing maximal sharing and everything is beautiful. But the thing is, if you introduce a cycle, you also introduce bottoms. Any cycle, if you have a cyclic reference in one of these comonadic infinite spaces, then as soon as you try to pull out a cell that's involved in a cyclic reference, there's no way for us to detect that, except for GHC does some magic and solves the halting problem and tells us that we get a loop exception. So the answer to this question is I went down this road for a little while trying to figure out how I could, inside of Haskell code, detect that we were involved in a cyclic reference and figure out, oh, we're in a cyclic reference, so just return nothing. Like put the whole comonad inside of or put the maybe monad inside the comonad and always return nothing whenever we end up having a cyclic reference. And I've managed to show, and the details are in the thesis, which is upcoming in the spring, that without using unsafe features, you can't do this and maintain the same computational complexity of this evaluate function. And Ed is making a face like he doesn't believe me.
No, I'm actually just wondering if, not with an actual Haskell comonad. My question is if you can do it with a comonad over a Kleisli category of something like maybe.
Maybe.
So you work in the Kleisli category, maybe. You look for comonads on that category. And then you can have comonads that have effects in maybe.
Oh, okay.
That may be a path to get you what you want. I don't know if it'll work for your case, but it works for other things that I've needed to do that looked impossible first.
Okay, let's talk about that later.
Yes.
We've talked about these one-dimensional comonads, but I hinted or said that we were going to talk about multi-dimensional comonads because what everybody loves about spreadsheets is that they're two-dimensional. And if everybody loves one-dimensional spreadsheets, and if everybody loves n+1 dimensional spreadsheets, then everybody loves any dimensional spreadsheets, right? So, nesting tapes within one another leads us to higher dimensional spaces that we can explore. So if you say a tape of A, that's an isomorphic to the line of integers. The tape of tapes is isomorphic to a space that's specified by two-dimensional coordinates, etc. So how do we actually talk about this? We could define a new type for each added dimension, but this carries an overhead of between O of n squared and O of n cubed boilerplate per dimension, which also really sucks, but in a completely different way. Or we could talk about composition. So there's this lovely little new type from data.functor.compose that lets us talk about the composition of functors. And for free, we get that the composition of two functors is a functor, the composition of two applicatives is an applicative, and what I want to be able to say is the composition of two comonads is also a comonad. So extract is really easy, because I can pull out the thing on the inside and then I can just extract again. But what's duplicate? Well, what can you actually do with a compose FGA? It's the same question as saying, what can you actually do with an f of g of a? So you can duplicate the outer layer, you can duplicate the inner layer, or you can duplicate both. And this almost gets us where we want. Because if we had some function that took an f of g of a and gave us back an f of g of a, then we would have exactly the function signature that we need, because we duplicate both layers and then swap the middle two. So let's actually try to find that. Whatever our question mark is, it probably has a more generic type. So I'm just going to look for something that just swaps the ordering of two functors. And then I'll say when you f-map it, then you get exactly the type of the thing that we were looking for. So we're looking for a question mark. Thanks to Google, I find two candidates. One is sequence A from traversable, one is distribute from data.distributive. So sequence A requires traversable and applicative. I like traversable, I like applicative. These are fun things to work with, but those two constraints maybe aren't applicable to the domain that we're talking about, because applicative means that the outer layer has to have pure. And pure is not necessarily something that we want to define for every comonad, because remember, pure is like return, and return is a monad thing, and not every comonad is a monad. And traversable is really a deal breaker, because infinite streams are definitely not traversable in any way that we really want. Unless you're traversing with a short-circuiting applicative or something like that, then you're not going to get to the end of an infinite stream anytime soon. So there's this interesting paper by Jaskelioff and Ripacek.
Yeah, we have to talk about the definition of traversable here, but
okay.
There's a subtlety.
Heads is wrong, so.
Huh? No. There's a subtlety and...
Okay. So there's a subtlety, so don't trust this slide. So distribute has the signature, if you ignore the constraints, it has the signature we're looking for also, but it requires distributive. So what's distributive? It's sort of the same question as what can you do under a functor, because distributive G is talking about the G on the inside. So in order to implement this swaparoo kind of thing, we've got to know how to talk about things underneath a functor. And the only thing you can really do underneath a functor is fmap things over it. So distribute, this is my intuition for how should you go about defining this distribute function. If you start with an f of g of a, you create a g with an f of g of a in every hole in g. Then, for each f of g of a on the inside of g, you navigate to a particular focus using fmap to sort of pass your navigation commands down through the functor, and you fmap extract to eliminate the inner g. And as a result, what you get back is a g of f of a. So, if you plug the whole thing in, requiring only that your inner comonad is distributive, you can get the composition of two comonads. And I was talking to Ed about this, and apparently there's a whole host of different ways that you can compose different comonads.
There was a paper by Mark Jones and Luc Dupont-Shiel from '93 called Composing Monads, where they went through most of those.
Right. So this is only one of many, many ways to do these kind of compositions. So currently if you import, I haven't fixed the library yet, but currently if you import the library, it defines a really, really, really general instance, which you may not want if you want to compose things otherwise. I'm going to fix that.
There's another observation about how to think about distribute, which actually goes back to a couple slides you had, a slide you had a couple slides ago.
Sure, which one?
Which is, if you look at distribute itself, distributive is actually the thing that I can say in Haskell 98. There's actually a stronger claim that you can make about every distributive functor, and that is that it is isomorphic to a function from some x.
It's representable.
Yes, okay. all distributive functors are actually representable functors in disguise.
Ah, okay.
We just don't tell you what the representation is. There exists a representation for every distributive functor.
Okay.
Okay, and so if you look back at your slide a couple slides ago when you talked about the shape of tape.
The shape of tape.
Where you had tape is, there you go, you just passed it. Tape, this one. Tape of A is isomorphic to integer to A. The representation of your tape is integer.
Right.
And therefore tape is actually the co-writer comonad in disguise.
Right, yeah.
For integer, that's all.
Yeah. So where was I? Yeah, so you can get this definition of the composition of two comonads, and you can get a distributive instance for tape just by sort of applying this intuition that I was talking about to tapes. So you say, start with a tape of tapes of A, then create a new tape with one of these tapes in each hole, and then navigate to a particular location in the outer tape, and then eliminate the inner tape. It all just works, and that's what this definition is about. So the story so far is we have efficient evaluation. We can take anything that's Comonad apply, and we can take this space of functions that reference a whole space of values and turn it into a space of values in a way that's maximally sharing. we have elegant composition. And so I got to this point where I had figured these things out, and I thought I could really make a library out of this. This is kind of cool. There's a shark in the water. Because I started to want to do things like this. So I wanted to count how many times something was composed. And so I defined this type family, this closed type family that would count how many layers of compose I had on top. And then I had a class that would take a thing and it would tell me how many things, but of course it required this language extension, which, this language extension. Because I did this thing. I did this very bad thing where I had to select my instance based on a constraint, and I had this universal instance that would match any f. Not fun. So, GADTs to the rescue. When are they not to the rescue? So instead of having this composed new type, you put the depth of nesting in the types. Effectively, you put, what I did is I made the type contain a SNOC list of all of the layers of functors that we put in the thing.
And now there's no objection to you having that Comonad lying around.
Yes. Well, unless somebody else wants to use my nested thing and define other. What's that?
The abstract data type was the G.
The G where?
Generalized.
It was just G and GADT.
Oh yeah, generalized abstract data, algebraic data types. So what I can do here is I can use the extra power that GADTs give me to construct this first parameter to my nested type that tells me what are the actual ordering of the things nested. So some examples of this. If I have just the list containing 1, then specializing to int, that would be maybe list of int. But if I apply this flat constructor to it, then it's a nested flat maybe list of int. So I've peeled off the outer maybe and stuck it into my list in the type. Then if I call nest on that again, I have a nested nest flat maybe list of int. So if you look at the type, it goes maybe list int. And this means that now I can define a functor instance for every nested flat f, and a functor instance provided that f is a functor and nested f's is a functor for a nested nest f's f. So that means that as long as all of the functors, as long as all of my layers are functors, then the whole thing is a functor. And I can do the same kind of definition for all of your favorite type classes, comonads, applicatives, traversables, distributives, etc. So the takeaway is by adding more types, you can match on types and not constraints. The base case is flat, so rather than every type being a base case, so there doesn't have to be this universal instance that forces you to match on constraints. And we don't have to use overlapping instances. We escaped the shark. So, if we actually want to be using these spaces, we want to be talking about references into those spaces. So, what's in a reference? Well, in spreadsheets, which are my sort of driving metaphor for all of this, you can have relative references or absolute references. So using data kinds, what I'm going to do is I'm going to say a ref type is either relative or absolute. And a ref is either a relative reference or an absolute reference. And secretly, under the hood, they're just ints. So further sort of specialization, we're going to be talking about successively nested tapes. Like these are all like metric spaces, and specifically they're all spaces that are isomorphic to functions from some n-length tuple of integers to the things that are contained within them. And what I wanted to be able to prevent, and the reason that I ended up using these types here rather than just having ref be a regular algebraic data type, is I wanted to prevent you from combining two absolute references. Because I want to be able to say something like add a relative reference to an absolute reference. But if I have two absolute references, there's really no good semantics for what it means to take those two and squish them together. So, and this is a sort of design pattern that I ended up using a lot in this library, which I think is really useful, is define a closed type family that defines the type behavior of a type class, and then use it to constrain any possible implementation of that type class. So if you look at this, there's no possible way that I could provide a definition for combine of two absolute references, because that type family just does not have a case for it. So the closedness of the type family can be used to sort of infect type classes, which themselves are technically open. And so really, it's a nice way of enforcing laws on type classes, I think. Or specifically enforcing laws about what are the allowable instances. We can define lists. I'm calling these conic lists. I've seen them called T lists. I've seen them called F lists. Basically, all they are is it's a heterogeneous list, except that everything in the heterogeneous list is inside of some functor F. And a list of references is just a heterogeneous list where all of the things are either a relative ref or an absolute ref. And then in type, we get a type level list that tells us which things are absolute and which things are relative. And we can talk about combining those things together. And I have this ampersand operator, which clashes with lens. I'm sorry, Ed.
It's a type of, oh, you know you have to turn on one too.
What's that?
No.
And so as a result, we have this class, which is, again, this trick of constraining the class by the closed type family. And with a suitable definition of names, we can say things like below by 3 and right by 14, which is a two-dimensional relative reference. Or column at 9,000 and above by 1, which is a relative reference in the first dimension, but an absolute reference in the second dimension. And their types reflect that. But we can't say column at 5 and column at 10 because that doesn't make any sense. And that's a type error. So with these kind of references, we can take things out of a space of some dimensionality. We can view infinite views of streams in a particular dimensional spreadsheet. We can go to a particular location. And we can insert things into one. And I've elided the type signature of insert just because it's a little bit complicated and I don't really feel like talking about it. But if you want to ask me, I'm happy to talk about it, but just not right now. So where are we? We've got this efficient comonadic fixed point that requires us to have zip. We've got that distributive comonads compose with one another. We've got that dimension polymorphism needs this kind of type indexed composition if we don't want to feel bad about ourselves. And that heterogeneous lists can be used to unify absolute and relative references in a type-safe way. Comonads are pretty cool. So I'm going to show some cool things you can do with comonads. So Fibonacci numbers are the sheet, the one-dimensional sheet, and this is using a bunch of like sugar that's defined in my library, where everything to the left of what I'm talking about is 1. So like the default value is 1. That's what sheet 1 means. And then everything to the right of 0 is equal to the cell left by 2 plus the cell left. And this is using some overloading of functions as numerics, thanks to, what is it, data.function.numeric or data.numeric.function, something like that. Basically, it just means that if the domain of the function is numbers, then we can add the functions together. And if you slice this, you get this, and it's fast. It's a memoized Fibonacci function, just as you would hope, because we went through all that effort to make sure that our fixed point was memoizing. And you can do that in multiple dimensions. So like Pascal's triangle, which has been my like go-to example for a kind of cool Comonadic computation, is defined like this, where you say everything all the way to the right on the top row is 1, everything vertically in the first column is 1, and then everything in the space below those is equal to the thing above, cell above, plus the thing to the left. So it's really kind of a tilted Pascal's triangle because the top of the triangle is the upper left-hand corner. So if you look at what this actually looks like when we evaluate it, this is the top. And I was talking to a couple of people. Of course, we have to talk about Conway's Game of Life, because what comonadic thing would be complete if you didn't talk about Conway's Game of Life? This is the entire implementation of Conway's Game of Life in this framework.
Just looking at the three-dimensional sheet.
Yeah, so Conway's it's kind of an interesting way of talking about Conway's game of life, because instead of saying we define this two-dimensional thing, we define this three-dimensional thing where two of the axes are space and the other axis is time. So you can talk about time slices by slicing the sort of like if this is like the four-dimensionalist view of the universe. The history, the future is all fixed, pun not intended. And so to talk about successive time steps, you just slice out a particular slice of the sheet that it represents a particular time slice. You slice out a finite chunk of space that you're interested in, and you ask what it is. And this is parameterized over the life rules, so you can plug and play your own like neighborhood parameters. So one example is a glider, which so zeros, O's here represent live cells and X's represent dead cells. And I defined a little printer function, which is really short and sweet, but I didn't want to put it on the slides, which does this. It's a glider. So, one more thing. This type signature that I was showing you here, for evaluate, it takes a W of WA to A to a WA, can actually be generalized to this. So what I've done is I've just inlined this F functor here, and what that allows me to talk about is kinds of referential structures where you've got one sort of line of reference going one direction and one line of reference going another direction. That is to say that if I want to reference some field of my neighbor going to the right, but some other field of my neighbor going to the left, as long as there's no cycle where I reference my neighbor's A field and then my neighbor's A field references my A. If my A field references my neighbor's A field, but my neighbor's A field references my A field, then that's a problem. But if any individual chain of reference works out okay in a lazy sense, then it's totally okay for me to have one sort of direction of references going one way and another direction of references going another way. And what I'm going to show is that this can be used to express a really cool problem. So Chris Dunn has this blog post called the Twitter water flow problem, and he uses lobe and a bunch of different other sorts of things to solve this problem. So basically, the parameters of this problem are you've got this one-dimensional landscape of ground levels, and it rains an infinite amount onto it and then drains off, so that you get a certain number of these cells filled with water. And the question is, how do you efficiently figure out what's the amount of water that fills the whole thing, that fills these puddles? How much water is left in the thing? So one solution to this is you do a scan right with minimum and a scan left with, and a scan left with minimum, and then you take, with maximum. You do a scan right with maximum and you do a scan left with maximum. That is to say, you take the cumulative maxima going in one direction and the cumulative maxima going in the other direction. And then if you take the minima at any given point, you zip those two together with minimum, what you get is you get a list where each element is the minimum of the maximum to its left and the maximum to its right. That is to say, the height of the minimum peak that the water level must be bounded by. And that allows you to solve it in this efficient way, but it requires these two different directions of scan. And so what I thought is we can put those two scans together into one sheet that talks about all of this. So, and Chris Dunn says, actually shows a comonadic solution, but it doesn't use comonad apply. It just uses wfix, and so it suffers from the exact same problem with sharing that I was showing before, where you get this explosion of no sharing whatsoever, and so it's super, super, super slow. So here is an implementation of the water flow problem using the stuff that I was working on. And it's really exactly like I described it. I say, I've got this maxima function, which takes an integer, and then it returns a pair of functions from a one-dimensional sheet of pairs of integers to integers. And what that means is each one of these things says, all right, I've got some height here. My left-hand element is either equal to the left-hand element of my left-hand neighbor, or it's equal to the height of my ground here, depending on which is the maximum. So that's my left scan. And also my right-hand element is equal to the maximum of whatever my ground height is here, or my neighbor's right-hand element. And then this ground thing is sort of the default, because once you go off the edge of the map, the maxima ought to be 0. So if you map this function over the initial list of heights that we get, and then we inject that into a sheet where the default is this 0 ground thing, and then we use this evaluate f fixed point, we view right across it, and then we fold with min, we subtract out the heights, and then we take the sum. This is exactly how you express this problem in words when you're, or more or less, when you're talking to someone about when you're talking to someone about, like, what do you actually mean when you talk about solving this problem, this is pretty much what you say, or at least this is pretty much what I say. So you can quibble with me about whether you think that this is actually really close to how you want to talk about this, but I think it's pretty close.
I'd say it's co-close.
It's co-close, which in the world I'm working with is co-good enough. So if you actually input this example that he has, just put this list of numbers in, you get 10. And if you want to count that, that's what it is. And he has this benchmark where he takes a random vector of length 10,000 and times how long it takes to solve the water flow problem for it. It takes me about 0.12 seconds. His lobe function on vectors takes about a tenth of that amount of time. I'm guessing that if I used some of the optimization techniques that we were just hearing about, it might get a lot faster, but I haven't tried this yet, so I may very well do that. And that brings me to the end of my talk. I'm currently on Hackage. However, the new stuff that I just showed with the water flow problem and the inline functor stuff is not yet there because I have to update a couple of other packages, and this is all super new stuff, but it will be there shortly, and if you want me to email you when it is, let me know. And I'm also on GitHub, and the GitHub repo does have all the new stuff. So suggestions, bug reports, and pull requests are very welcome. And that's my thing.
I do have a quick question if you go back a couple of slides. Sure. So with pair itself, when we were looking at pair.
When you say a couple
here,
here?
right there,
Yeah.
exactly. So pair itself is also a distributed functor, right? So
I don't think I use that fact.
exactly, and that is actually my question. At this point in time, do we actually need to do this exotic thing with f of w of f of w, or can we get away with the fact that pair itself is also a comonad, and it's a comonad that distributes over the other comonad that we have available to us here.
It's a
So
comonad in the sense that you would extract the first element?
Well,
Just
no, it's a
arbitrarily?
function that's isomorphic to a function from bool.
Mm-hmm.
And
What's extract for pair?
take true, take false. Pick one. Pick
Oh,
one,
yeah,
and then
sure,
you
yeah.
comonad apply to glue them together with and or.
Right.
It's just like when we go to do integers, we extract at 0, and when we duplicate, we get a function from integer to a function from integer that we take the two integers and we add them together.
Yeah. Mm-hmm.
The question that I was basically getting at is, can we do the same thing with just wfix, or with just your whatever we want to call your
Evaluate,
your
that's what I
fix?
called it. Yeah, this guy.
Yes, that will, by the way, find its way into Comonad very soon.
Yes.
Because that is a much better fix than the two that I have in there.
I'm not sure. The trick that makes this guy work and do what I want it to is the fact that I've got a function. I've got this sort of w of f of a to a inside every cell of this functor. Mm-hmm. So it's the two-layered structure that lets me.
Well, if w of f is a comonad, then I can do the extract to peel.
Mm-hmm. But you
Yeah.
don't you. So you're saying instead of talking about this, say let W in the above
Be
be
WF.
composed WF.
Yes.
Yeah.
Where F here is now pair, which is
Mhm.
also a form of the co-writer Comonad, just like W is.
Right. And because you can distribute them over one another.
Yeah, they distribute very easily because they're both function spaces, right?
Yeah. And that's actually this is real. I mean, really the
And so it may
trick
be that evaluate F, just the evaluate F use cases that you have may just be evaluate use cases.
I think so. I think
That would make me feel really good about that construction.
I'm gonna try that. I think you might be able to do it, and it's kind of neat because if it's distributive, it is distributive. So that means that you're talking about, oh, it's a left scan and a right scan, and you put them together. But then you can actually just say distribute, and then you get the pair of the right scan and the left scan.
Mm-hmm.
So that's kind of nice.
And you can probably use the fact that we can build a Comonad transformer from it and just extract, or just lower from
Oh.
WF to F.
So you'd have like a sheet T Comonad
Yes.
transformer.
Exactly. The sheet T monad transformer would just be the existing co-writer T, which
Okay.
is NFT.
Right.
So if you look at NFT integer, that is your sheet T, just as a function rather than as a
But with different asymptotics.
well. So that was the first observation, and the second one that came to mind was that did you see I wrote a series of blog posts on FP Complete about cellular automata, and part
I
3
did.
talked a bit about the relative motion versus absolute motion in cellular automata
Oh, I don't
as the
remember
difference
that.
between store and co-writer.
Okay.
So that point has come up in that context, although it was a very limited interpretation there, but
Okay, yeah, I'll have a look at that. I'll see if I might be able to port some of that stuff over.
you may be able to steal some tricks from that.
Yeah.
Those are the two things that left out of it. Otherwise, great.
Yeah.
So the examples you were giving were sort of with this streamer Comonad. Have you done any examples with other Comonads?
I've done some stuff with tree-ish and tree-zipper-ish Comonads. They tend
Even like powers of them?
Yeah, I mean, the thing is you don't get to observe the efficiency as nicely because here we've got this space where it's obvious when the sharing is happening, and with the tree-ish ones, you've got a tree structure, so it's already not that nice. But yeah, I'm really interested to hear about other Comonads that might be cool to put into this framework because like all of the reference stuff is specialized to the tape-ish Comonad stuff. But beyond that, everything else here is really generic, and I would really be interested in seeing other applications, other spaces where this works.
So there's
I mean, I suppose anything you can encode as a series of integers.
Well, yeah, but it could be anything that's a Comonad apply gets you the efficient evaluate, and anything that's distributive as well as being Comonad apply gets you the ability to stack dimensionalities. So if you can find other interesting structures that have those properties, please email me and I will put them in my paper.
So there is a connection actually to so Tarmo Stallo at one point in time did a couple of talks on ideal monads, and at one point in time I think I packaged up co-ideal comonads somewhere.
Okay.
And a co-ideal comonad is a comonad that you can break down into what you would extract and all the other stuff.
Okay.
Okay, so the ideal monad, what you have is the return case and all the other cases, and then you have a law for how you build up the bind. And if you look at your tape, the tape that you're using can be viewed as what you extract, the A,
And everything
all the other
else.
stuff.
Yeah.
Right? And so you can view the fact that what you have is your sheets form a co-ideal comonad, because they happen to be a co-free comonad. If
Right.
you choose the right base functor, right, the pair of two lists. The reason that that's interesting is that co-ideal comonads always compose.
Really?
So when we talk about the fact that monad products exist, but monad coproducts don't necessarily. When we talk about comonads, comonad coproducts or comonad coproducts always exist, but their products don't.
So you,
right?
you can always take the sum of two Comonads, is what you're saying?
When they're co-ideal.
When they're co-ideal. Okay.
Yes. Well, you can always take the sum. You can always do the. You can always take the sum because you can extract from each other whichever one you have. Or
Right.
whichever. There's a little formula.
Oh, sure, yeah. If you've got either stream of A or tape of
Yes.
A, then
And it's
yeah.
like, and with the monad, you can do both, and then just
Mhm.
throw away the other computation.
But there's not a unique one for products on Comonads because you could. Which one do you?
But when you do the co-ideal case, there is a nice canonical notion of how to layer the Comonads together.
Okay.
Okay, and so that may give you another way to think about your Comonad sheet because it should coincide with the definition that you get by using the distributive law.
Coincide.
Yes.
All right.
On that note.
On that note.
That's the outside, go inside.
Oh gosh. Any other questions?
So for composing comonads, you don't need that G is distributed over all functors, like
Just over
distributed
this one.
is just over the one. So then you could talk about F and G that distribute over each other in the right way, and then you're probably not limited to only representable functors.
No, and that is actually the case that Mark Jones and Luke Dumonchil went through. They went through and they talked about given a functor and given a monad and any pointed functor that have appropriate distributive laws, like either that f of g distributes to g of f, or that FGF can absorb one of the f, or there's like, they give like 3 or 4 different conditions, and that gives you about half of the things that give us monad transformers today. And the other things seem to be things like Kant, or other cases where you get a distributive law like thing where if you have any adjunction where f is left adjoint to g, then gf is a monad, and you can shove any monad in the middle of that, so you get gmf is also a monad. That's where we get state d. So all those constructions, most of those were sort of seen in advance back in '93 by Mark B. Jones and Luke Dumonchil. So,
But you could, two pair comonads.
So talking about comonads that are distributive over one another, but not distributive over any functor.
yes.
Not distributive over everything, because you don't need everything, you just need.
Yeah.
Yeah, if you look at my recursion schemes
overkill to
package,
talk about everything.
my recursion schemes package just gives you a composable vocabulary for distributive laws.
Okay. Yeah, I should see if I can integrate that.
So that would give you the ability to talk about particular pairs of
Hmm.
comonads that don't work with. It may kill your nice, pretty little nested structure, but you can think of it as in general that you just want to work with comonad transformers because a comonad transformer is a way to take a simpler comonad and add more structure.
Sure.
So if you just talk about an nft of nft of nft or whatever, as you're adding integers
Yeah.
to your thing, that is your higher dimensional sheets.
Yeah, it kills a couple of the nice little functions that I have. So like insert the function that I didn't want to show the type signature for because it's gnarly. Can take something that has the right dimensionality, but is maybe different types as long as the individual base types are insertable. And like if I've got a list of lists of A, then I can insert that into a 3-dimensional sheet. But it could also be a list of streams of lists of A or something like that. And it's a really nice thing, but it only works because I can determine the dimensionality. Yeah. Or I could use overlapping instances.
Or you could use lenses into the actual. We'll have to talk about that part now.
Ooh, that sounds interesting.
All right. I think that's everyone. All right. Well, thank you.
Thank you.